But next week we have another practical on pH, so we need to beaver on. Okay, so for the pH, we said we can calculate the pH. pH equals minus log of the proton concentration. Yeah, you remember that? So for example, if we have a strong acid, very strong acid, for example, HCl plus water gives us H3O plus, and I can also write here H3O plus, doesn't matter, plus Cl minus. Okay? We said usually, conventionally, the pH scale goes from 1 to 14. Why 14? What is so special about 14? It's the ion product of water. You are absolutely right. And now in plain English? Oh, well, I tell you what. Let's wait for a minute. What the ion product of water is, yeah? So let's just for the time being say 14 is a magic number when it comes to pH. So, very quick revision. HCl plus water, what is the acid? HCl, why? It can donate a proton. What is H2O? It is the base. And here's the acid. Okay, now according to that, can you please calculate what is the pH of a 1 molar HCl solution? pH equals? Say again, loud. 0.1. Why? Minus log of 1 molar. Well, the molar we don't write, really. What's log 1? 0. So the pH would be 0 in this case. Ooh. I asked you the last time, can we have a pH smaller than 1? Yeah. Obviously we can. Right? Just simply 1 molar hydrochloric acid. Well, actually, usually when you buy hydrochloric acid, it is a 10 molar solution. What's the pH of a 10 molar solution? pH equals 1. 1 or minus 1? Minus 1. Ah. Minus 1 because log of 10 is 1, but we have a minus in front of it, so the pH is minus 1. So this shows that pH can be negative. Fair enough. There's no rule saying that a pH can only be positive. It can also be negative. Ha! Here it comes. A really tough nut for you. I have, instead of hydrochloric acid is boring. I have H2SO4, sulfuric acid. And again, it's a very strong acid. It's called a diprotic. Or some people also call it a dibasic. Not entirely sure if I like this expression. Diprotic means 2 protons per each molecule of H2SO4. Dibasic means it needs 2 molecules of base to neutralize it. It's a little bit idiotic, but hey, we are biochemists. So, let's assume you have a 0.5 molar H2SO4. What's the pH? pH is 0. Why? There are 2 protons for each molecule of sulfuric acid. So what we have is pH equals minus log of 2 times 0.5. Yeah? Does that make sense? That was one of the questions that people found quite hard. But now it makes sense. Yeah? Are you happy with that? Wonderful. Now let's come back to this bizarre thing, this 14. In a way, it sort of bothers me. And sorry, what's your name? Tanaga. What Tanaga said is, does it bother you that it's 14? Not really. It should bother you. Why is it not 42? You know what 42 is. It's the answer to life. It's the answer to life, universe, and everything. No? No. Okay. Douglas Adams. Yeah. You know? No. Okay, let's try that again. Hitchhiker's Guide to the Galaxy. Seffert Beeblebrox. Yeah. Yeah? Yeah. 42. Okay, you read the book.
Do I need to?
Huh?
Do I need to?
Absolutely. It is the best book in the world, in the galaxy, I would say. Right? So it's definitely worth looking at it. So why on earth is it 14 and not 42? Okay. Let's say we start from the very beginning. HCl plus H2O gives us H3O plus Cl minus. Now, the Cl minus, this guy here, can obviously act as a base. It can accept protons, right? Bless you. So we can write Cl minus plus H2O gives us what? It gives us HCl plus OH minus. Absolutely. Yeah, and this happens all the time in water. Yeah? Now, we do a really, really dirty trick. Are you up for that? Yeah, I thought so. We just add these both equations together. So what we get is HCl plus H2O plus Cl minus plus H2O. That's this part here. Gives us H3O plus Cl minus plus HCl plus OH minus. Okay? Now there's a lot of redundant stuff going on. Things that I don't really need, they cancel each other out. For example, I've got an HCl here, and I've got an HCl here, so I just, HCl gives HCl. So what? Who cares? HCl cancels out. Cl minus cancels out. So what have we got left? We've got H2O plus H2O gives H3O plus OH minus. Treason! Our acid has disappeared. Our HCl has disappeared. Our chloride ion has disappeared. And I can actually do that for whatever acid I want to do it. It's always H2O plus H2O gives H3O plus OH minus. Everything else just disappears. It's like a magic trick. Okay, now, you could argue, so what? Now let's write this a little bit as an equilibrium. We will talk about equilibria next term. We will talk about kinetics. But what happens actually is we can write this as a chemical equilibrium. So for example, we can write K equals the concentration of H3O plus times the concentration of OH minus divided by the concentration of H2O times H2O. Yeah? That is our equilibrium. That happens when the system has reached a certain state. And usually, what we find is that people lump that together because the concentration of water usually stays the same, stays constant. The water doesn't change really, unless you work in really weird systems, but we don't do that. Usually that is included in this dissociation constant. Very often this gets the index of W, Kw. So we can rewrite this Kw equals H3O plus times OH minus. Do we know the concentration of H3O plus or protons in water? Loud? It is 1 times 10 to the minus 7. 1 times 10 to the minus 7. And we know that for each proton that is generated, we also generate an OH minus. Right? So what is the concentration of OH minus? 1 times 10 to the minus 7. Yeah? So Kw equals 1 times 10 to the minus 7 times 1 times 10 to the minus 7. 10 to the minus 7 times 10 to the minus 7 equals kW equals 1 times 10 to the minus 14. Hey, we got 14. Now this thing is actually called, it's the, say again?
Ionic product of water.
It is the ion product of water. Now sometimes, as I told you, we like to abbreviate things. So therefore, instead of these 10 to the minus 14, and you know, with the typewriter, I told you that this was such a pain in the ass that I went super blonde and got stress highlights. We do the same thing as we've done with the pH. We just do the P. Which reminds me that I hope this lesson ends soon, because pretty desperate, but you know, let's not. So what we can do is we take both sides minus log. So we get minus log Kw equals minus log of 10 to the minus 14. And this one here is simply called Kw equals 14. So the ion product of water is 14. This is where this magic number of 14 comes from. But it has a far wider reaching consequence. If I go back to this one here, are you singing? Let's look at that. I said Kw equals H3O plus times OH minus. Now let's do this minus log of both sides with this. We get minus log Kw equals minus log of H3O plus. And now here comes rules of logarithms. The times turns into a plus minus log OH minus. Yeah? So, minus log Kw, we said, what is that is pKw. Number? What's the magic number? 14. Equals minus log proton concentration is pH. Plus minus log of hydroxide concentration. What would you call that? It is the POH. So pH plus POH always gives 14. So I can easily convert a pH into POH and the other way around. It's always 14. Does that make sense? If you think about it. Are you happy with that? If you are happy, I'm happy. So if you have a pH of 6, what is the corresponding POH? 8. 6 plus 8 equals 14. If you've got a pH of 0, what's the pOH? 14. It means 10 to the power of 1 protons plus 10 to the power of minus 14 hydroxide ions. Yeah? That is what pOH means. pH plus pOH is 14. And you can always convert them into each other. I have to let you into a little secret. I've been lying. Well, actually, strictly speaking, I haven't been lying. I just might make things a bit too simple. But you are all grown-ups, I assume. So I think you can handle the truth, can't you? What we have dealt with so far were very, very strong acids. So when we had HCl, which disintegrates into H3O plus Cl minus, this acid almost completely disintegrated. 99.999999999% of the acid was gone. So therefore, it was very easy for us to say, what happens? Well, almost all of the acid has dissociated. It's a very strong acid, which has a high desire to give off its proton. But life sucks. Very often we find that acids are not that strong. So, for example, let's say we have an acid. Let's call this guy HA. We add water. And what happens then is we produce H3O plus A minus. Now let's assume that this HA is not a very strong acid. Only a little bit will dissociate. I've upset him. Only a little bit will dissociate. So, for example, we start with 1,000 molecules of HA. And only 1 in 1,000 of these molecules will dissociate. So how many H3O plus have we got? 1. Because only 1 in 1,000 will dissociate. How many A minus do we have? Also 1. How many HA do we have left? 999. Exactly. We still can write our ion product or our dissociation for this. We can write K, and this time a little a because we are talking about an acid, equals H3O plus times A minus divided by HA. And here we said it's 1 plus 1 divided by what we have left is 999. Yeah? So our Ka in this case would be 1 times 1 1 Yeah, it's 2. Divided by 999. Well, it's pretty close to 1,000, isn't it? Yeah, it's 999, but it doesn't make a huge difference. It's close to 1,000. So that gives me 1 times 10 to the minus 3. Yeah? Does that make sense? Now what we can do is, again, we do this minus log. So we say Ka equals 1 times 10 to the minus 3. We take both sides minus log. And we get minus log Ka equals minus log 10 to the minus 3. I'll write that on another page. Minus log Ka equals minus log of 1 times 10 to the minus 3. Can you suggest a name for this? Loud? Yeah, it is the dissociation constant. And what was the suggestion here? It is called pKa. In this case, equals, what is minus log of 10 to the minus 3? 3. So for this particular acid, the pKa, HA, for this particular acid, the pKa is 3. Who gives a flying monkeys? Why should I worry about pKa's? What the heck? Actually, this pKa is extremely useful because it tells us something how strong an acid is. Let's have a look. Let's have another acid. Let's say HB plus H2O gives us H3O plus, oh God, plus B minus. And this is a stronger acid. Let's say half of the acid dissociates. It's stronger than the first one, isn't it? In the first case, only 1 in 1,000 molecules dissociated. In this case, half of the molecules dissociate. So if we start with 1,000 here, how many H3O plus do we have? 500. How many B minus do we have? 500. How many HBs do we have left? Also 500. Yeah? So let's write down our Ka for this particular acid equals H3O plus times B minus divided by HB. So we have 500 here, 500 here, 500 here. Actually, we can cancel that out. So Ka equals 500. Yeah? Now let's do our pKa minus log. And we get here minus log Ka, and I write this as pKa for HB equals minus log 500 equals, what do you get? Minus 2.69? So minus 2.7. Yeah? So in this case, the pKa is minus 2.7. In the case above, in the case of the weak acid, it was 3. So we can almost say, we can come up with a rule. What would this rule be? The higher the pK, the higher the pKa, the stronger, weaker? Stronger? Sam says stronger. Chelsea says weaker. What is it? Stronger or weaker? Oh, wow. The higher the pKa, okay, let's go back. We had a weak acid here, pKa 3. Because only 1 in 1,000 dissociated. Now, in the case of HB, half of it dissociates. Which one is the stronger acid? HB is the stronger acid, isn't it? So that's strong. So pKa is 3. Which one is higher? Which pKa? HA, because it's 3. The other one was minus 2.7. So, strong acid, low pKa. Weak acid, high pKa. So therefore, the higher the pKa, the weaker the acid. Does that make sense? Yeah? The higher the pKa, the weaker the acid. Actually, if the pKa is around 0, bless you, if the pKa is around 0, then usually people don't bother about it. So a pKa is usually only given when we are dealing with a weak acid. If it's a strong acid, we assume it is completely dissociated anyway. That make sense? Whew. Just stay with me for another 5 minutes, okay? Because here comes another piece of magic. And I really need to leave. Okay. Let's play a little bit with this concept. Again, let's say we have our weak acid, HA plus H2O gives H3O plus A minus. And we said we can write this with our dissociation constant with an equilibrium. Ka equals H3O plus times A minus over HA. Actually, it's not entirely true how I written it, because remember we did that 1 and 1, and then we had 999 here. So actually, I would need to write equals H3O plus. But in fact, I can write, because it's the same amount of protons that are produced with the A minus, I can write this number as basically squared. Yeah? Because the A minus is the same number as the H3O plus. But down here, I really should write HA minus what has dissociated, H3O plus. That's technically correct. But as we have seen, this bit here is not too different from this bit here. That's why I've earlier said, instead of 999, I just simply write 1,000. The rest, this one bit, that's for you for Christmas. It's my present for you. 1 unit. So I can write, actually, Ka equals H3O plus squared divided by HA. That's the starting concentration of the acid that I had. Because only so little will disappear. Now, are you ready for that? Here it comes. Drum roll. Let's take minus log of both sides. Minus log. Now the left-hand side is easy, isn't it? It's minus log Ka, which is pKa. Right? Equals minus log of H3O plus squared divided by HA. Now I can write this in a slightly different format. I can write this as equals minus log H3O plus squared. We know that a fraction I can write as a negative thing. So I can write this as minus, that's the fraction, minus log of HA. Okay? Rules of logarithms again. Now this bit here, I can write as 2 times minus log H3O plus. Plus log HA. Minus times minus equals plus. Okay? Happy with that? Who cares? Actually, it's great stuff. What is log H3O plus? What did we say that? What did we call that? It is the pH. Woohoo! So we have equals 2 times pH plus log HA. Let me write this, because this is something, it's like, roast beef with horseradish sauce and Brussels sprouts and red wine gravy. You have to roll that on your tongue, this equation, because it's so beautiful. pKa equals 2 times pH plus log of, I should write it really like that, HA, the concentration. Do you see the beauty of that? Probably not. But never mind, because what we can do with that is we can solve this equation now for pH. We can try to rearrange this equation so that we get pH on just one side. So we bring this to that side. We have pKa minus log HA equals 2 times pH. And if I want the pH on its own, I just simply divide by 2. So I end up with pH equals 1/2 of pKa minus log of the acid concentration. I should probably have another bracket here. Now this little bit of playing around gives us actually a chance to calculate the pH of a very weak acid. This is an equation that I want you to remember. Yeah? pH equals half of pKa minus log HA. This is the pH for a weak acid. We know that it's a weak acid because it has the pKa in it. For a strong acid, we don't need to worry about that. The pH for a strong acid we just simply can say pH equals minus log of the strong acid concentration. Got the brackets the wrong way round. So basically, if you have been given a pKa, you know it's a weak acid. Therefore, you know that you have to use this one here. Weak acid, because there's a pKa in it. If you haven't been given a pKa, you know it's most likely a strong acid, and therefore you have to use this one here. Does that make sense? So watch out for the pKa. The pKa tells you which equation you want to use. Does that make sense? Needs a little bit of digestion and a little bit of practice. So we will do some practice on Thursday where you can calculate these things. I shall see you bright and early or in the afternoon tomorrow. And don't panic. Mostly harmless.